Hello and welcome to the Analog Devices Precision Digital Isolation Technology training videos on the fundamentals of isolated gate drivers. This video is the first in the series and will go through the basics of power switch technology. We will discuss the need for gate drivers and review available devices used in power conversion as well as their drive requirements. We'll explore traditional power switches and newer wide bandgap devices, explain how they operate, and understand why gate drivers are needed to drive those switches. Gate drivers are used for driving electronic switches. Before we discuss the need for gate drivers, we need to review some of the available power switches. The most common switches used in power conversion circuits are the MOSFET and the IGBT. MOSFET stands for metal oxide semiconductor field effect transistor. The MOSFET has three terminals called the gate, drain, and source. IGBT stands for insulated gate bipolar transistor. Its terminals are the gate and emitter. Gate is the electrically isolated control terminal for either device. Both these devices are conventionally fabricated with silicon as the semiconductor. Due to the limitations of silicon-based power transistors, devices using wide bandgap material such as silicon carbide or gallium nitride are finding increasing acceptance. These devices can be operated similar to traditional semiconductors, but are used for improved performance. The traditional switches, MOSFET, and IGBT are voltage-controlled devices, which can be operated when a voltage is applied to the gate relative to the source or emitter. Due to MOSFET being a majority carrier device, it has a lower breakdown voltage to keep the on-resistance low. On the other hand, IGBT is a minority carrier device, and in high-voltage applications, IGBT is the device of choice because of its higher breakdown voltage. To maintain low on-resistance, the doping has to be higher, and hence the MOSFET can handle lower voltage before breakdown, whereas the on-state resistance for the IGBT can be kept low due to the conductivity modulation, which is the injection of minority charge carriers. The MOSFET can operate at higher frequency, whereas due to current tailing, IGBTs cannot switch as fast as the MOSFET. The trade-off is always between on-state resistance, breakdown voltage, and operating frequency when choosing a device in an application. Earlier, we discussed that silicon-based IGBT and MOSFET have their limitations, and that devices with emerging wide bandgap technology are finding application space. The wide bandgap devices are named based on the larger energy gap between the valence band and the conduction band of these materials compared to silicon. Wide bandgap materials such as silicon carbide and gallium nitride have bandgap which is about 2 to 3 times larger than silicon. Insulators have bandgap energy above 4 eV. Wide bandgap devices require higher energy to go from the off state to the conducting state, Thus, these devices can tolerate a higher electrical field without breakdown. This has a profound effect on the voltage levels and the frequency that these devices can be operated at. Being able to withstand higher electrical field strength allows these devices to be used at higher voltage for size when compared to traditional devices. To get similar blocking voltage, smaller, wide bandgap devices can be created. Since smaller devices switch faster, higher edge rates can be obtained. As shown in the diagram, if edge rates are higher, the transition time for voltage and current is lower, and hence the switching loss is lower. The devices can be operated at higher frequencies, which leads to use of smaller passive components and a more compact solution. Wide bandgap devices also have low on resistance, leading to lower conduction losses in the on state. The bandgap energy reduces with temperature, but since wide bandgap devices inherently have a larger bandgap, they can be operated at higher temperature. The application space for devices is different with respect to voltage and frequency, even though there is an overlap. For low voltage, higher frequency operation, the device of choice is the MOSFET. For higher voltage, lower frequency operation, IGBTs are used. Due to the limits on fabrication technology with gallium nitride, presently those are only used for lower voltage, high frequency applications. And GaN devices are used as a replacement for the MOSFET in high performance systems. Meanwhile, silicon carbide is substituted for the IGBT in higher voltage application spaces due to the silicon carbide's advantage of higher frequency operation. Having looked at the various types of switches, we now look at how to switch them. This figure shows the switching transitions during the turn-on of a 60-volt MOSFET when driven by a microcontroller GPIO. The waveform, VDS, is the drain to source voltage of the MOSFET, and VGS is the gate to source voltage of the MOSFET. The structure of the power MOSFET is such that the gate forms a nonlinear capacitor. Charging the gate capacitor turns the power device on. The device will start conducting when the gate voltage crosses the threshold voltage. When operating the power device as a switch, voltage sufficiently larger than the threshold voltage should be applied between the gate and source or emitter terminals. When driven by a gate driver, as seen in the figure on the right, the time to charge the capacitor is greatly reduced due to the higher drive current supplied by the gate driver. This reduces the switching time. CMOS TTL logic levels may be required. The gate driver will perform this task of level shifting from the digital logic levels, as well as providing higher drive strength. The discharging cycle of the device is quite similar, such that the device turns off and a large voltage is blocked across the drain and source terminals. Analog Devices has many digital isolators that provide trusted safety and data integrity. To learn more, watch the next in our Precision Digital Isolation video training series on the fundamentals of isolated gate drivers. Click on the link below or visit analog.com/iCoupler.